Hello, and once again welcome to SST Chemistry channel. We were in the previous video on this particular topic, fine structure in atomic spectra. Spin orbit coupling will be discussed in details, that is internal Zeeman effect, and also the actual Zeeman effect with spin orbit coupling, anomalous Zeeman effect. This is the part 2 of this topic. And in the previous video we learned that fine structure in atomic spectrum comes for two reasons. Do you remember? That is, one is high resolution spectrometer, when you are improving the power of the analyzer, the monochromata, the separator, prism turned into a high power grating. Then you are using high resolving power instrument. That is high resolution condition. You can get splitting of spectral line, and that we shall study in details. That is due to LS coupling. And also it is sometimes called internal Zeeman effect. I always avoid this term because once I coin the term Zeeman, it may lead to some confusion to the young minds, as if there is some external magnetic field. No, there is no external magnetic field. But like Zeeman, when a magnetic field influences another magnetic field, in the same manner, the internal magnetic field influences the spin magnetic field. That is why it is called internal Zeeman effect. And we will also see how Zeeman effect will be found for those high resolution cases where you have a spin orbit coupling. Let's start. This will be the 17th lecture on atomic structure. This is a repetition that spin orbit coupling that is noticed, observed under high resolution conditions. Forget about the external magnetic field. Only high resolution condition if there is an unpaired electron. If there is no unpaired electron, still there is transition, then also you don't see any LS coupling. When there is an unpaired electron like sodium 3s1, hydrogen 1s1, such cases spin orbit coupling will occur only under high resolution spectrometry. In species where there is net spin momentum along with orbital momentum, the two momenta vectors add up vectorially, and the resultant gives the net or the total angular momentum, right? And now this is denoted by the J vector. L is the angular momentum due to orbital motion, also called the orbital angular motion or the azimuthal quantum number, angular momentum. This is the orbital angular momentum L, which is equal to L into L plus 1 root over h by 2 pi, and this is S, the spin spin angular momentum. These are the two momentum vectors, and this is S into S plus 1 square root h by 2 pi. You know, the S is the number of S is the total spin. S is the total spin. Now the J vector is now important. Supposing this is an L vector due to orbital motion, and this is the S vector because it is also spinning about its own axis. You might be surprised that this orbit has been shown little tilted. This orbital motion of the electron is shown little tilted, right? And this is the J vector, and this is the resultant, not clearly shown. It's not seen because it is a copy pasted diagram. You can mark here there is a vector that is the resultant of these two. right? These two vectors are following head to tail. So this is the triangle law. This is the resultant, right? This J vector will be interacting with the external magnetic field. This is the direction of the external magnetic field. If at all, there will be Zeeman effect. But I am not yet started Zeeman. Zeeman already we have done in our previous video, that is normal Zeeman effect, when there is no LS coupling. Now here the abnormal Zeeman effect or the anomalous Zeeman effect with LS coupling will be doing after we thoroughly understand what is LS coupling. It happens at high resolution condition and the two vectors now will produce the resultant. This is the J vector, and the L vector and S vector, they won't independently interact with the external magnetic field, if at all there is there. Now the L vector and S vector, they go away, they vanish. In their place, the resultant vector takes the command, and that interacts with the external field in the Zeeman effect to produce different non-degenerate quantum states. You understand? This is called spin orbit coupling. Yes, I was saying why this is rotating in a different plane, right? Let us forget about that, because the electron is not remaining fixed in its orbital. It is changing the orbital. That it is undergoing precessional motion, like a top precessing in the gravitational field. So the electron also is not only rotating, but also the axis of rotation is precessing, right? And this is also precessing. So doesn't matter, you forget about the precision. Just think that this is the L vector, the angular momentum, orbital angular momentum vector. This is the spin angular momentum vector. This is the J vector, the resultant vector. Nothing else. You now poke your nose into that. Yes, the resultant vector now interacts with the external field, if at all there will be Zeeman effect, to produce non-degenerate orbitals. We'll talk about that later. Note that under ordinary resolving power, low resolution condition, this coupling is not observed for hydrogen-like species or any other species. Even if having one unpaired electron or more than one unpaired electron, the LS coupling is not observed because the power of the separator, the monochromata, is not high. But under high resolution condition, yes, LS coupling and its effect is observed. Let's do that. Again, I am showing you the picture that I showed in the previous video, that this is simply a source of the sample where it is thrown into the monochromata. Here we are taking high resolution condition where a highly powerful grating is used to increase the resolving power of this separator, monochromata. This is the main component of the spectrometer. You know that. Now there is no external field here, but you are using high resolution spectrometer. Then you will find splitting, if at all there is an unpaired electron, and that is what we sometimes call internal Zeeman effect. So I always recommend not to use the term Zeeman here to avoid confusion. Simply LS coupling. It is due to high resolution spectrum splitting occurs due to LS or RS coupling, right? And here this is the anomalous Zeeman effect that we'll be studying, where this is an external magnetic field, and inside that the sample will be kept, where the sample will be in the influence of a magnetic field. It should be weak. Magnetic field, and the radiation that it is emitting will be passing through a separator or a monochromator, and this time a high resolving power grating, and you will find there will be further splitting of lines due to magnetic effect. You forget about this interference patterns, forget about that. We're talking about lines, taking the picture in a photograph. Right? So let's proceed. Let's first proceed with no magnetic field, no Zeeman. So I definitely feel little awkward to use the term Zeeman here, because I am following the names that are already given by atomic physicists or the researchers themselves, the quantum physicists themselves. So I am not a expert in the field to disobey what has been already named as internal Zeeman effect. But I will refrain myself to use the term Zeeman here in mere LS coupling under high resolution condition. In the absence of magnetic field, just let us read out, we know everything. In the absence of magnetic field, this spin-orbit coupling can produce non-degenerate states from a subcell. This is called internal Zeeman effect. This takes place under high resolution condition. We can say that the orbital magnetic dipole moment, internal dipole moment, magnetic field, will interact with the spin magnetic moment to split into two non-degenerate quantum states, one with spin up, other will spin down. That is the quantum state of the orbital. With the spin up, spin down, there will be two states, right? Number of non-degenerate quantum states produced from a subcell is given by the J quantum number. That is the total angular momentum quantum number, both orbital as well as spin, which is obtained from L and S quantum numbers as given below. I have given you a simple relation how to find the number of J quantum numbers that will ultimately interact later when we talk about Zeeman with the magnetic field, or it will give you how many quantum states it generates even without external magnetic field. Only due to LS coupling it produces two states, L plus minus S. S is the total spin. Obviously in most cases it is half, only one unpaired electron, and L, if it is P, then 1. If it is S, there is no question of any internal Zeeman effect or any LS coupling, because if there is no internal magnetic field, if L is equal to 0, there is no question of influencing the two different spin states of the electron spin. So no question of any other state. So S orbital has a unique state if there is no external field. But P orbital, if at all it has one unpaired electron, will be split into two states. One characterized by J equal to L plus half, the other L minus. I mean, yes, since one unpaired electron plus half and the other L minus half. L is 1 for P subcell and 2 for D subcell and so on. So one represents the spin up and the other spin down. The electron spinning clockwise and the other electron spinning anti-clockwise, spin down. The S orbital does not have spin orbit coupling. Remember, does not have spin orbit coupling, as its orbital momentum is 0. The no internal field to split the so-called external field, that is spin magnetic field, into two states. It is unique state. Each S orbital has a unique quantum state if there is no magnetic field. Under high resolution condition also s orbital is unique, but p orbital will be split into two quantum states characterized by j is equal to plus 3 by 2 and minus plus 3 by 2 and plus half. Always j values will be plus, right? In this LS coupling, I'm talking of LS coupling. I'm not talking of further splitting in the presence of magnetic field. That will be different. It will have negative values. But in pure LS coupling, J values will be positive. Right? If supposing it is a D subcell, L is equal to 2 plus minus half, and there is one unpaired electron, so 2 plus half is plus 5 by 2, 2 minus half is 3 by 2. Right? Only two states, spin up and spin down, characterized by J value 5 by 2, 2 plus half, and 3 by 2. That's it. And S is always half. There is no plus minus. So no coupling at all. No LS coupling. So only half. Now let us apply this to the L alpha line, that is the first line of the Lyman series under high resolution. That was having, you remember, in normal Zeeman effect it was showing 3 lines Zeeman, because the P was split into 3 equally spaced quantum states, Px, Py, Pz, and there are all the 3 transitions were allowed and we are getting 3 lines, right? But now we are looking to no magnetic field but under high resolution condition. No magnetic field, no Zeeman, but internal Zeeman. That is under high resolution condition, it was found that the L alpha line split into a doublet, 2 finer lines, doublet. Because, yes, let me read out, with high resolution spectrometer, each line of hydrogen spectrum, this is a general statement. With high resolution spectrometer, each line of hydrogen spectrum gives finer lines. Sometimes doublet, sometimes quintet, 5 lines, sometimes more lines. We can't say always it is a doublet. In some books, some literature, I found that in high resolution spectrometer, they have written that each line will be split into a doublet. It's not always the case. It is the case with L alpha line. It's not also the case with the H alpha line, the first line of the Balmer series. So into multiplate, you can say into multiplate. Same multiplate word was coined in Zeeman and also in under high resolution spectrometry. No Zeeman, also multiplate, not we can say doublet every time. The first Lyman series from n is equal to 2 to n is equal to 1, we know. That is from 2p to 1s, 2p to 1s, splits into when there is no external field, then the s 2s to 1s, that the question of the 2s to 1s transition doesn't arise. In fact, we do not take 2s different from 2p, because there is even the subcells are degenerate. In magnetic field, the subcells will be non-degenerate. So what happens here now? So I'm taking n is equal to 2 and n is equal to 1, right? So 2p has 2 quantum states due to LS coupling. L because S will not have any coupling because it has a zero orbital angular momentum. Got it? So only 2p, which has got a non-zero magnetic moment, orbital angular momentum and orbital angular magnetic moment, and that has coupled with the spin vector to produce a J vector, and it has got 2 values, 1 plus half, 1 minus half, plus 3 by 2, plus 2, 3 by 2, plus 1 by 2, all plus. So S orbital does not take part in LS coupling, as its L is equal to 0, L vector 0. So it has a unique quantum state. Now, you might be thinking that what about 2s? When 2s remains in the same energy level as 2p, and why we are not taking another? Because the energy level is same. There is no splitting of the subcell unless there is a magnetic field. So we are completely forgetting 2s, only taking 2p, which has a net orbital angular momentum that will couple with the spin to produce j plus 3 plus half plus 3 by 2, I'm sorry, plus 3 by 2 plus 1 by 2, right? And it will come to the first cell, because that transition will be in the ultraviolet region. As you know, it is an ultraviolet region, L alpha. All the L series, they fall in the ultraviolet region, not in the visible region, as you know. So let us see what happens. You know, the selection rule that is followed for LS coupling, where there is no L, no S, there is J, that delta J, the change in J value, so the del J will be 0 or plus minus 1, not plus minus 2, 0 plus minus 1, with the exception that J 0 to J0 is forbidden, right? So 2p 0, supposing there is a J0 value, here we don't have a 0 value, supposing we will get later in abnormal Zeeman effect, anomalous Zeeman effect will find the J value 0. But here only LS coupling, there will be no 0. All plus positive values, plus 5 by 2, plus 3 by 2, plus 3 by 2, plus half. So in that case, there is no 0. But if there will be 0 value, later we will know, when magnetic field will come, there will be 0 value. So 0 to 0 transition is not allowed. Now see, under high resolution spectrometer, spectrum, the L alpha line, just L alpha line, which was a singlet in the low resolution condition, the spin orbit coupling was not observed. Now it will be observed. It will be a doublet. Why? Because the P has two quantum states due to spin orbit coupling, 3 by 2 and 1 by 2. We have forgotten 2s. You can say, why are you not saying 2s to 1s is forbidden? Delta L is equal to 0 is forbidden. I can say that. But I am now saying that there is no such SP, there is no magnetic field, means and there is no SP division. They have the same energy. So therefore I am, and moreover it is not having any spin, any orbital angular momentum vector. So I am just neglecting 2s. If it is a case of Zeeman, then I would say 2s to 1s transition is forbidden as delta L is equal to 0, right? Now let's see what will be the number of lines from a single line in the Balmer, the first Balmer line, that is H alpha line in the Balmer series, which falls in the orange region of the visible spectrum, will be split into how many finer lines under high resolution condition. Have a look. High resolution condition, no external field. Can you remind me how many lines were produced in the Zeeman effect, normal Zeeman effect of the H alpha line? Again 3, triplet. Why? Remember, there were 15 transitions from 3D to 2P, the allowed transition, out of which 6 are rejected. They are forbidden by selection rule. And out of the 9, only 3 different transition energies relating to, corresponding to delta M minus 1, delta M 0, delta M plus 1. So you have 3 lines, right? Remember, that was Zeeman effect, normal Zeeman effect. But here the splitting is not any magnetic field. It is only due to LS coupling. that I am going to highlight you that here there will be 3D because 3D in case it is a Balmer series, it is 3D to 2P. That we know the transition between 3D to 2P. 3 to 2. In between the subcell, the energy will not correspond to any UV value or visible value. In this case, it is visible value. Unlike sodium, where subcell to subcell transition will involve energy in the visible region, sometimes in the UV region, but in case of hydrogen atom, the cell to cell transition will have energy value corresponding to visible or UV or IR, right? So if we consider 3D to 2P, ignore the other, and again the same thing will say 2P to 2P transition is disallowed, right? 2P to 2P is disallowed. I'm really constrained here to apply the selection rule that here 2P had 2. But I still say that this transition, though can be possible, will not lead you to produce any spectral lines in case of hydrogen atom, because the energy gap will be very, very small. I guess even it will not fall in the IR region, so less, right? But we are looking for the first line of the Balmer series in the orange region. Our interest is not 3D to 2P. If these 3S, 3P, 3D are not non-degenerate, they are degenerate, then what will happen to other transitions? Why not 3D to 3P? If they, but they have the same energy value, and what I was saying is even if there are same transition values, but this 3D to 3P, that in between these subcells belonging to a particular cell is not happening. So we consider the 3D, what happens to the J values, and 2P, what happens to the J values. Now since it is 2, d orbital is 2, then 2 plus minus half, so plus 5 by 3, plus 5 by 2, this is the J value, the subscript, and d 3 by 2, plus 3 by 2. And S, yes, there is S, 3S, there is a 3P, so they have all merged, 3P and 3D, all the 3P, they come under here, 3 by 2 was there. Yeah. Remember, P is there, P is there, but they are the same. Now I understand. These things are so very interesting, and I assure, I confide with you that while preparing this material, this content, I had to go through several times to see how the evolution happens. Now see, I have written 3 by 2, but that also the J value same means whether it is D or it is because they belong to the same cell, degenerate. It's not a magnetic field, so both will be together the same level, that is D 3 by 2, and P also has 3 by 2 and 1 by 2. So this will be a doubly degenerate, right? But one level. Similarly, the previous case where we were talking about 2S will have only plus half. That plus half is already there. So this will not only be 2P half, but also 2S half, the same energy value. So it's not a new energy level, right? So now I got it that 2S and 2P, they are degenerate, but P will be split, S will be splitting into only one. There is no LS coupling, so it is only one state, that is half. J value is half, and J value same means belonging to the same cell. The subcells are degenerate. In that case, these two J values, they represent the same quantum state. 3 by 2 is another state. Similarly, here what has been written here, that D 5 by 2 is unique, and then 3 by 2 has 2, I mean from the P side and from the D side. D 3 by 2 is there, and P is already there. We have done for P is 3 by 2 is there. So here also these two represent the same energy level, and here the P half, the S has one quantum state, 3S has one quantum state, and P has 2, 3 by 2 and 1 by 2. From the D side 2, from the P side 2, and S is 1, right? So out of these transitions, this transition is not allowed. This 5 by 2 to half, the J value differs by a factor of 2. 5 by 2 minus half, that will be 2. 4 by 2 is 2. Delta J 2 is not allowed in any transition. J value delta J should be 0 or plus minus 1. So this transition is disallowed, but all other transitions are allowed, and therefore you find the corresponding 5 peaks with the different intensities. Still then, the probability of transition will not be same. The intensities are different. So 2 prominent peaks will be found, and other 3 are very short, and this one is almost buried in the baseline, right? So you got it. So under high resolution condition, the H alpha line of the Balmer series produces 5 lines due to 5 allowed transitions. There are 3 J values from the third cell. There will be 3 J values. From the D side, 5 by 2, 3 by 2. From the P side, 3 by 2, half. And from the S side, half. So these levels are doubly degenerate, the J level, and this is doubly degenerate, and this is unique level. So these are the 3 energy levels in the third cell and 2 energy levels in the second cell. S also you can write as half here. No problem. Same energy level, because there is no magnetic field, right? So there are 6 transitions, out of which 1 is forbidden. So 5 lines. Got it? No magnetic field. Last. We are now coming close to our climax scene. The climax scene will be anomalous Zeeman effect, where there will be external field, there will be LS coupling, high resolution on this side, high power diffraction grating, and this side magnetic field. Then let's see how many lines it will generate. Now before we do so, let me tell you that transition energy in hydrogen or hydrogen-like species will produce lines in the UV visible region by electronic transition from one principal quantum number to another principal quantum number. 5 to 2, 5 to 4, 5 to 1. These fall under hydrogen spectra. They change in principal quantum number, as well as there will be change in L value and M value. And we have to apply the selection rule to reject some delta M cases, some delta L cases, and take. But delta N can be any value, right? So, but in multi-electron species, the transition of electron from one subcell to the other, that will demand that will throw the energy which will be in agreement with UV visible region. For example, in sodium, one electron in the 3s level will be excited to 3p, and on de-excitation it will give the characteristic radiation, and on splitting in a normal LS coupling we will find that, I think we have not done that, we will do now, that it will form a doublet, D1 and D2 line under normal LS coupling, high resolution spectrometer, no Zeeman effect, right? So subcell to subcell, 3p to 3s, that transition will give you the spectrum radiation. But for hydrogen spectra, after all the subcells are degenerate. 3s, 3p, 3d, they are degenerate. But due to spin orbit coupling, there will be different states. We have just now discussed, right? So for them, transition from a higher principal quantum number n to a lower principal quantum number n has to be there to give you an emission belonging to the visible UV region, right? Because the gap between 3s and 3p in a multi-electron system, 2s and 2p, 4s and 4p, that is good enough for UV visible emission. But for hydrogen spectrum, you know, the gap between two different quantum levels, principal quantum levels, n values, that will correspond to the visible or UV radiation, right? Now see, we have not yet finished the internal Zeeman effect or simple LS coupling under high resolution condition. We shall be applying to a multi-electron species like sodium. I could have finished from here only hydrogen spectra, but I am interested to extend our discussion to a multi-electron species like sodium. Now let me read out how the sodium spectrum under high resolution condition will give you a doublet. Spin orbit coupling produces non-degenerate, these are all repetitions. The spin orbit coupling produces non-degenerate quantum states from a subcell at high resolution condition. We can say that the orbital magnetic moment, is a repetition, can interact with the spin moment to split into two non-degenerate quantum states, that is L plus minus S. Number of non-degenerate orbital states produced from a subcell is given by the J quantum number value, which is obtained from L and S according to the relation J is equal to L plus minus S. Now in sodium, you know, the configuration of sodium is the neon configuration 3s1. It is the ground state ZS, and in the flame it goes to the 3p level. There is a good gap between 3s and 3p. It is a multi-electron species. As such, due to different penetration power, 3s and 3p, they are of different energy values. They are not degenerate like hydrogen atom, right? So this gap, when it goes to the excited state, the electron now is in the p level, and then when it de-excites from p to s, 3p to 3s, not 2s, 3p to 3s, the same quantum level, then it gives the energy photon that corresponds to the visible region, and one is D1, the other one is D2. Now see, what are the J values for the P subcell? P, L is equal to 1, and you know the relation L plus minus S. So 1 plus minus half. So again, just like the L alpha line splitting in case of hydrogen spectrum, also 3 by 2, 1 by 2. So there are two states for P, 3p. They are no longer degenerate and no longer 3 orbitals. You know, 3 orbitals will come only when magnetic field will come. But here the P, all the P, 3p orbitals, whatever, they will couple with the spin, and this is the guiding formula L plus minus S. That is two quantum states, one representing spin up, the other spin down. But it's the orbital quantum state, right? Taking spin into account, the spin and the orbital motion together into account. And for 3s, no coupling. As long as there is no magnetic field, whether internal or external, no coupling, only one quantum state. So this transition will give you one line, the lower wavelength line, and this is the higher wavelength line. I'm sorry, this will be the higher wavelength line and lower wavelength line because the energy is more, lambda is less. This is energy is less, lambda is more, right? Now, once again, I'm showing you here, this is 3s half, the J value is half here, and this, there are 2p, 3p, 3 by 2, J value 3 by 2 half, and both the transitions are allowed. 3 by 2 minus half, this is 2 by 2, 1, and half minus half, it is 0. So J0 to J0 is not possible. The difference is 0, but J0 to J0 is not possible, but that will come only under magnetic field conditions. No 0 will come under normal LS coupling, all positive. Now, in sodium excited state, the P has 2 quantum states, plus 3 by 2, plus half. So there are 2 states for the P subcell, having 1 electron, even in the absence of magnetic field. There is no Zeeman effect, internal Zeeman effect. And so 2 spectral lines, one D1 representing this one, because this one having higher energy and lower wavelength, and 5896 angstrom corresponding to the lower energy transition from P half to S half, right? This is called the internal Zeeman effect. It's a repetition. Are you not bored? Okay. Then the last, the climax, the anomalous Zeeman effect, where there is spin orbit coupling in the presence of external field here. Then further splitting of lines occurs due to magnetic field. LS coupling is there, high resolution is there. At the same time, there is extra magnetic field, it will further split those already J values we have got due to LS coupling will be further split into other levels. I'll tell you how you find each J value in the absence of magnetic field will split into how many non-degenerate energy levels. There is a rule. That rule is it has 2J plus 1 in the presence of external magnetic field. Just like in case there is no spin coupling, the value is 2L plus 1. In the presence of LS coupling, the number of non-degenerate quantum states in a particular J value in the normal LS coupling will have now 2J plus 1 J values, where the J value starting from plus J to minus J, or from minus J to plus J with an increment of 1. Plus 1, plus 1, that will go via 0 and it will come to the other, either starting from minus come to plus, or from plus to minus via 0. Now, for example, the J value in the normal LS coupling is 3 by 2, plus 3 by 2. Then how many non-degenerate quantum states that will be generated from this one quantum state in the presence of external field? It will be minus 3 by 2 to plus 3 by 2. You add 1 to this, you will get half. Again add 1 to this, you get plus half. Add 1 to this, 3 by 2. So there are 4 quantum states coming from this J value 3 by 2 that is only due to the LS coupling of the P subcell. Similarly, the J is equal to half of the P subcell will split now into minus half, plus half. Start from minus J to plus J, and once you add 1, it will become plus half. So only 2 states. So J half will be now having 2 substates, and J3 by 2 will have now 4 substates. In that level, J3 by 2 has 4 substates, and J half of the P subcell will have 2 substates, plus half, minus half. Right? Now the P subcell has now 4 substrates. 4 plus 2, 6 subsets. 4 from J is equal to 3 by 2 and 2 from J is equal to half. Now the J values are different in the presence of external magnetic field. Note that this is very important. The S orbital, which was having one unique quantum state, will now be split into 2. Plus minus half will be applicable now here, because although the S orbital has no internal magnetic moment, there is an external magnetic moment. right? So for internal magnetic moment you write 0, but the principle plus minus half will be applicable. So you have two states, plus half and minus half, spin up and spin down. Those will be two distinct levels will come up only when there is an external magnetic field. So to do that, again for L alpha line, do you remember what happened to the L alpha line in presence of high resolution spectrometer? Not Zeeman. Normal Zeeman was a triplet. Forget about it. Normal Zeeman, we have finished it long before. Now we are talking mere LS coupling, high resolution, which was a doublet. Remember this two transitions. I have kept this again for comparison, right? This is normal high resolution spectrometer giving a doublet. Now 3/2 will be now converted to, will be split into 4 non-degenerate quantum states, plus 3/2, plus half, minus half, plus 3/2, minus 3/2. And then this P half will be split into 2 energy levels, right? Plus half and minus half. So this P subcell, which was having only 2 states, now have 4 plus 2, 6 states. And 1s, which has only one unique state, no LS coupling, because the internal field was 0, but here due to external field there is a coupling, between external field and the spin field, and it will be a doublet. 2 non-degenerate quantum states, plus half and minus half. Now tell me, how many total transition energies will be produced? Now from the P, which has got now 4 sublevels, to this plus half is 4 this to this 4, and this to this 4, 8, out of which 2 are discarded. From 3/2 to minus half, this will be the delta J value of 2, which is disallowed, forbidden. So if you, out of the 8, 2 are discarded. 2 are discarded and 6 remain. So P 3/2 to 1 S half. This one I am talking of, this to this, which was 1 line, this one, that will be 6 lines. And there are, 4 into 2, there are 8 possibilities, out of which 2 are forbidden, and there will be 6 lines. And this line, this line is now having 4 lines. This has now 2 states, this has now 2 states, all the 4 are allowed. So these 4 allowed transitions and these 6 allowed transitions. So there will be altogether 10 lines. Can you believe that it was 2 lines, a doublet under simple high resolution spectrometry, no field, no Zeeman, but here there will be 10 lines. From 3/2, 2 plus minus half, there will be 8, out of which 2 are discarded. Which are the 2 discarded? Can you again tell me? Now from here to here, 3/2 minus 1/2, so that is 2/2, 1, that is allowed, and which one? From this to this, 3/2 to half, 3/2 minus half, that is 4/2 is 2, is not allowed. And what? Yes, from minus 3/2 here, 2 plus half. So minus 3/2 minus half, again minus 2. So this transition is not shown, minus 3/2 plus half, and plus 3/2 minus half. This transition is not shown. The 2 are discarded, 6 are allowed, 6 lines. And here from 2p plus minus half to 1s plus minus half, there will be 4, all allowed. Delta J remains within 0 and plus minus half. 0 and plus minus 1. So altogether 10 transitions. 10. Can you believe how interesting it is when you Zeeman found under high resolution condition 10 lines, under low resolution condition, how many lines? 3 lines, which we have done before. Under low resolution condition, 3 lines, Zeeman, and on high resolution condition, anomalous Zeeman, 10 lines. Because the LS coupling along with the magnetic field, external magnetic field, 10 lines. And only high resolution L alpha will be giving a doublet. Only high resolution doublet. And that doublet will be converted to 10 lines under magnetic field, that is anomalous. Same thing will happen in case of, but Balmer series is very complicated. It was, you remember, there was 5 acceptable lines here. You have seen there will be 5 under high resolution condition, and that each state will be further split into 5 by 2. So this state will be 5 by 2 minus 5 by 2 minus 3 by 2 minus half plus 3 by 2 plus 5 by 2. So there will be how many states? Plus 5. And similarly 3 by 2 will have 4 states. 1 by 2 has 2 states. So tell me how many states we get. And then this also. So many transitions, out of which you have to discard many due to selection rules, and therefore it is very complicated. So I have not discussed this, the anomalous splitting, a Zeeman splitting of the H alpha of the Balmer series. It will be many lines. It's very complicated. Now let us wind up our discussion with the anomalous Zeeman effect in sodium spectrum. I told you before some time that sodium has only 2 lines, D1 and D2, only under high resolution condition, and due to 3 by 2, 2p 3 by 2 to 1s, I'm sorry, 3p, I'm showing you once again, 3p 3 by 2 to 3s. I told you this is the transition between subcells, not between principal levels, because this 3p by 3p 3 by 2 to 3s a half, that is one, the D2 line, as a D1 line, and this is the D2 line, 3p half to s half, similar to L alpha. In L alpha it was 2 to 1. The principal quantum numbers were different, but here it is 3 3 3, same. P level is 2, that is doubly non-degenerate, and this is unique, no magnetic field. But in presence of magnetic field, just like we had seen in the case of L alpha, this 3 by 2 will have 4 states, and this half will have 2 states in the respective region, and S, which was unique, now will have 2 states. So in the same manner as L alpha line of Lyman series, same manner, out of the 8 transition, 2 will be discarded, 6, and 4 all our transitions are allowed. So altogether 10 lines, 2 lines, a doublet D1 and D2 will be split into 10 lines. Is it not interesting? The same yellow region. So we come to the end of our program. To know whether we have correctly remembered all these 2, the video before this and now, whether we have understood correctly, we have remembered, and I will be also in the description box, I have given you the link to get my PPT, the PowerPoint study material or the contents that I have prepared. It is for you, and you can just have a look to the link that I have given, the PDF file link. You can get it and read again and again. If you are a physics student somewhere in the undergraduate, you can take the benefit of it, because this is not in a curriculum in school level. In India, so far as I am concerned, I know for sure that in Indian schools there is no curriculum stipulation that this anomalous Zeeman effect, its this theory and its basics are not included in the syllabus. But anywhere other than India, if you have, I doubt, or in undergraduate level, if you have, you can have a look and can give your critical comments on any point that I have told which will you think is not acceptable, or I have done some error in judgment or in concept. I will be extremely happy to rectify. Now, these are the three things you have to identify, you have to assign. Whether the particular multiplet that I have talked about from here downwards, whether it is a high resolution spectrum, simply only RS coupling, that is internal Zeeman effect, or it is a normal Zeeman effect, external magnetic field, Zeeman effect, no LS coupling, or it is LS coupling with Zeeman effect, that is anomalous Zeeman effect. You have to identify. I will be giving how many? I will be giving 8 questions. Number 1, here it goes. Doublet in the L alpha line of Lyman series in hydrogen spectrum. If you are getting a doublet, 2 lines, then what kind of spectrum will it be out of these 3? Pause this video, think a while and answer. The answer will be, I am writing down the answer here. The answer will be, tell me, only doublet, only doublet. That means P 3 by 2, P half to S half. Then only there will be doublet, L alpha line. Otherwise, it would be 10 lines. It is, if it is a anomalous Zeeman with a magnetic field, you would have 10 lines. I have seen that. So this is simply high resolution spectrum. This is A. I am writing A. A means it is a high resolution spectrum only. No Zeeman, nothing. You can call it internal Zeeman, no doubt about it. Yes. Then triplet in L alpha line in Lyman series. Triplet, same Lyman series, same L alpha line, but it's a triplet. Tell me, triplet. Magnetic field, if there is a magnetic field, then Px, Py, Pz, there will be 2L plus 1 different non-degenerate quantum levels in a subcell. So there are 3 Px, Py, Pz have 3 different states, and it will come to 1s. So there will be 3 transitions, right? So it is normal Zeeman effect. Triplet means normal Zeeman effect. That means it is B, right? Then coming to triplet in the H alpha line in the Balmer series. I also remind you that it is a triplet, not that it is having 3 transitions. I mean 3 transitions. There are 15 transitions from 3D to 2P, and out of which 6 are discarded. Out of 9, there are only 3 transition energy values. Therefore triplet. So this is ordinary Zeeman, that is normal Zeeman effect, that is B once again. No LS coupling, low resolution condition, normal Zeeman effect, low resolution condition, only Zeeman effect. Then D1, D2 line of sodium spectrum. Only 2 lines means it is high resolution and no magnetic field. It's not anomalous Zeeman, nothing Zeeman. It's simply high resolution spectrometry. A. 10 lines in sodium spectrum. Same sodium, 2 lines converted to 10 lines. Remember? You remember? You know, the 3 by 2 giving how many states? 3 by 2 plus half, minus 3 by 2, 4 states. And it will come down to 3s plus half minus half. So there will be 8, out of which 2 are discarded, 6. And then from 3 plus minus half, s plus half minus half, 2 states, to 3p plus minus half, 3 half, there are 2 states, plus half and minus half, 3p plus half, 3p minus half. Because each quantum state will be split into 2j plus 1 substates. So 2p plus half, 2p minus half. 3p plus half, 3p minus half. 2, 3s plus half, 3s minus half, 4. So these 4, this 6, 10 all are allowed. So it is nothing but anomalous C, anomalous Zeeman effect. Zeeman effect with LS coupling C. 10 lines in the L alpha line hydrogen spectrum. You know, 10 lines means it has to be magnetic field. So many lines cannot come without magnetic field. right? Then in that case, we have anomalous Zeeman, because only LS coupling of the L alpha line will give you only doublet. And the same way as sodium spectrum gave 10 lines in the anomalous Zeeman effect, same thing will happen. This is again C. And 5 lines in the H alpha line in the Balmer series, that is nothing but high resolution spectrum. I told you that high resolution LS, simply LS coupling will make in hydrogen L alpha line between 3D and 2p. This 3D, there will be how many states? D2 plus minus half, that is 5 by 2 and 3 by 2. And also there will be 3p plus 3 by 2 plus half. So 3 by 2, 3 by 2, they are degenerate. So 3D, 3 by 2 and 3p, 3 by 2, they belong to the same quantum states. And then 3D half, because 3p half and 3s half. Do you remember that? This is 3D, this is 5 by 2, and this is 3D 3 by 2 as well as 3p 3 by 2. This is there is no D, D is gone. This is 3p half along with 3s half, because there is no coupling, LS coupling in the s orbital, so only one. So these are the 3 non-degenerate states, and it goes to the this is 3D, and this third cell, and this is second cell. This is 2p 3 by 2, this is 2p 1 by 2 as well as 2s 1 by 2. So there will be how many possibilities? 6 possibilities, out of which one is spin, one is quantum forbidden selection rule wise. So we are left with 5 transition energies, so 5 lines. That is normal. This is A. That is, what is A? It is high resolution spectrum, only LS coupling. And if it is simultaneously given a magnetic field, then so many lines we have to find out theoretically. Each state will be having 2j plus 1 values, from minus j to plus j with 1 increment and all that, right? Now second question, if you find that splitting of spectral lines do not occur in high resolution spectrum, what conclusion you derive? You are using high resolution spectrum, still single line is remaining as a single line. What inference you will draw? You will say that there is no LS coupling then. There is no unpaired electron. So the spin moment is 0. It is all are paired, but transition is occurring with the same singlet state, going to the higher level with the same spin, so that there will be cancellation of the spin magnetic moment. So the net spin is 0. In that case, you say that the spin is 0. The net spin is 0. So LS coupling is not occurring at all. There is no LS coupling. Right? How did you like my program? How did you like my program? And thank you very much for patiently hearing or watching till the end of my program. Bye-bye.